Okay, transformer is a, yeah, big equipment and close. We cannot have a look inside the transformer to see what happening inside the transformer. So condition-based maintenance is very important for such equipment. For transformer, uh, the DGA is a very important methods to have the information uh, inside the transformer. So, what is the DGA? Why and how we do that? DGA is the dissolved gas analysis. We do the analysis for oil in transformer to see the content of gases inside the oil, and based on that we can determine what happening with our transformer. Why we do this? Because almost all the failure or the problem, the faults inside the transformer will relate to high temperature. Inside the transformer we may have the hot spot. We may have loose connection, causing the higher temperature on the connection point. We can have the in abnormal conduction, or even we can have the arcing. With all force will always associate with high temperature. Then the thermal force uh, always associated with gas generate. The gas generate inside the transformer because of the decomposition of transformer oil, and some case is come from the aging, the decomposition of the insulation. So the content of gases inside the oil will indicate, and that information will help us to predict the situation, the faults may developing inside the transformer. In normal situation, the gas generated from oil and insulation is dissolved into oil and exists in oil in ppm level. So that is for a normal developing a normal transformer, or in case of four phones is a normal developing in transformer. But in some critical situation, the gas is the oil is not able to contain all the gases generated from the force. So in that case, we may see in some gas bubble in in the oil. So in normal operation, if you go to the backhoe relay, you see in the side glass, and you find that there is some gas bubble inside, or the oil level in the side glass decreasing day by day. That is a critical indication, a critical sign indicating something uh, critical happening to our transformer. Okay, so in details, what gas generated in the oil for DGA, for indicating the faults in the transformer. So here, typically we have five gases generated uh, by oil. Uh, and exists in oil in ppm level. This gas is hydrogen, methane, ethane, ethylene, and acetylene. So it's based uh, on the temperature the gas will generate in oil. Uh, if you see into the molecule of each gas, so in chemically, the combination of the molecule of gases must be follow the chemical rule. The example here is that we have hydrogen. We have with hydrogen we have one bond to connect to hydrogen atom to create the hydrogen molecule. Methane we have one carbon and four hydrogen. Every carbon we need four bonding. So four bonding connect four hydrogen to one carbon, making methane molecule. For ethane, we have two carbon and six hydrogen. Ethylene, more special, we have two bonding between two carbon and four bonding for four hydrogen. Acetylene, we have three bonding connecting three carbon and two bond connecting two hydrogen to create the acetylene molecule. The bonding between two carbon is stronger than the bonding between carbon than to hydrogen. Then here, from hydrogen to methane, ethane, ethylene, and acetylene, we have stronger bonding between the atom of the molecule. The stronger bonding that means we need higher energy to generate the gas from oil. So higher energy that means we need higher temperature to generate the gas from the oil. So with hydrogen, a lower temperature. If you see into the chart on the right side, you can see that the lower temperature will require to generate hydrogen from oil. Then for each gas, we all have the peak on each gas corresponding to specific temperature generating the gas from the oil. For hydrogen, a bit special. Typically we have hydrogen generated at lower range of temperature, but hydrogen may come up again. Here you can see at very high temperature, like in a critical situation like arcing, it generates both acetylene and hydrogen. So hydrogen is can be used as a common alarm for DGA for indicating a general problem in the transformer. So uh, in conclusion, we can say the force in the transformer will generate the gas inside the oil. Then based on the content of the gases dissolved in the oil, we can understand what force is now existing, what force is developing in the transformer. Of course, there are some very special situation. For example, with hydrogen, it sometimes may not come from the force. hydrogen may be generated because of some pain in the insulation under the chemical reaction with additive and oil may create hydrogen. Anyway, uh, however, the content of such a generation is very small and stable. So, suddenly increasing of the hydrogen, it always indicating something wrong with the transformer. Beside of the five gases generated in oil indicating the force, we have some other gases also we consider during the DGA. The gases is we consider is the CO and CO2. CO and CO2 is not directly come from the force, but CO and CO2 is come from the paper, the cellular material aging and breakdown. Why the cellular material, the paper in transformer breakdown, mostly is because of the attack from high temperature in oil. It's caused the paper become more brittle and aging. Then uh, under the accelerating factor for the aging of paper is oxygen, is moisture, acid level in oil. Is that factor will increasing the aging rate of the cellular material. Then also in converse direction, the decomposition of the paper of the cellular material also create the moisture in oil, create the acids and uh, oxygen in create the moisture and acid in oil. So it that is a closed loop. The oxygen uh, will accelerate the aging of the paper. Then the aging of the paper also creates the moisture, create the acids. Then moisture and acids in oil again accelerating the aging of paper. So normally we consider the ratio of CO2 per CO in transformer. The normal ratio is in between 3 and 11. Then if the ratio is less than 3 is indicating a high rate of aging of paper. Then if the ratio is higher than 11, it's indicating um, the problem of thermal degradation of the paper. So if CO and CO2 limit is over the limit and the ratio is outside of the between 3 and 11, we can have some rough information of the cellular aging in transformer. The other two gases we consider in the transformer is O2 and N2, it's oxygen and nitrogen. So how it's come from? Uh, Oxygen and nitrogen is come from the atmosphere. Then it's a sign indicating that the oil is exposed to air. How the oil can exposure to air? Typically on our transformer, It could be from the oil leak. So in the main tank, in the conservator, if there is a gap, or in on the flank connecting the piping, if the gaskets is not tightly closed, and the oil can leak out. If the oil leak out, the oxygen, nitrogen can leak in, and even the moisture also can leak in, then increasing the oxygen and nitrogen content in oil. Another issue is on high voltage and big transformer. We have the rubber bladder inside the conservator. Then, in case the bladder broken after many years in operation, the back can become broken. Then the oil can contact to air, and increasing the oxygen and nitrogen in oil. Uh, the problem of oxygen in oil is oxygen is accelerating the aging of the cellular material in the transformer and shorten the lifetime of the transformer. But another more important is if oxygen and nitrogen uh, in exist in oil, also a sign indicating some leak, some gap, not fully tightening in the main tank or in the flank, in the bushing, then oil leak, then the rainwater, the moisture can get in the transformer. Then moisture is a very dangerous factor in the transformer. Then some case with oil leak and high moisture in transformer, it's caused the BDV of the oil. BDV is breakdown voltage of the oil reduced. So for a transformer, the BDV should be higher than 40 kilovolt. If the BDV is too low, the insulation of the oil become best. Then at some certain level, the discharging or arcing discharging or even the totally burning the transformer might happen. So on oxygen and nitrogen, we can have some information of the faults developing of the problem for the transformer. That is all the gases we consider with DGA. Uh, we with five fault gases: CO, CO2, O2, and N2. Some example of failure in transformer here. The example with T2, thermal faults. T2 is a thermal between 300 to 700 degree. So a very typical problem with T2 is the connector, the loosen in the connector, loosen the bone and nut, will causing the high temperature in the connector. Then by DGA we can detect that with T2 fault. Another case with OLTC problem, we find with acetylene increase, then ethylene increase. So acetylene, here, acetylene is we have three bond between two carbon atom and two bond to connecting two hydrogen atom into the molecule. So acetylene will need a very high energy to generate from oil. That's why here in the chart on the right side, you see the peak of acetylene generated in oil is at a very high temperature because it's need large energy to generate. So the content of acetylene in oil is a critical issue. Typically, if you do the DGA, the content of acetylene should be in somewhere less than 1 ppm. So if you see acetylene increasing, that means some high temperature faults happen in the transformer. So most of the case is arcing. So here the problem is the arcing in the connector, the arcing in the contact of the OLTC. So we found with the acetylene and ethylene level increasing in DGI. Okay. Then for the interpretation of the ppm of the content of the gases in oil into the falls, we have some methodology and some standard. Here with the international standard IEEE C57 C57104. We have two versions. The previous version is a 2008. Uh, this one, this table is come from the old version. So here we have the limit of the gas content in oil for condition of the transformer. So we can see if the gas over this limit for each gas, then we can have the level from 1 to 4, indicating the criticality of the condition in transformer. However, on the next version, this standard in the new version in 2019, they re-innovate this table uh, and consider two more factor. That these two factor will impact to the limit of gas content in oil. That is the transformer age in year. So the older transformer, the content in oil might be higher, and O2 per N2 ratio this is the factor indicating the exposure of oil into air. So we consider two more factor may impact to the content of gases in oil. This table is based on the survey with a lot of transformer and based on 95% percentile of the survey of the transformer population in the survey. So if the limit of the gases over than the value in this table, that means the transformer is belong to 5% population having the problem. Then if the limit here is over, we need some further methods, some further investigation to find out the root cause and to have more information for the developing fault. Then another index, another value that we also consider is the TDCG, is the total dissolved combustible gas. That is including CO. So the combustible gases is hydrogen, methane, carbon monoxide, ethylene, ethane, and acetylene. So the total number have we have a general information for the situation of gas generated in transformer. Then the absolute limit of the gas in of the gas content in oil is here. But one more important thing is how the content of the gas increased compared to the last analysis. So we need a trending to see how the gas content in ppm increasing in oil. That also a very important information to do the assessment of the in the DGA. So generally, if TDCG increasing by 30 ppm per day, that is a critical situation, a critical condition of the gas generated in oil. Then here we have the method to interpret the result we have from the lab. That is IEC 60599. So with this standard, we consider the ratio of two gases. We have the three ratio of gases to be considered in this standard. That is acetylene C2H2 per ethylene C2H4. Then we have the ratio of methane per hydrogen. Then we have ethylene per here we have the final ratio. We have ethylene per ethane. Then based on the ratio of these two gases, we have three ratio. Then we plot the ratio into a 3D coordination. Then with this standard, in the 3D space here, in the standard, we have some cubicle defined by the standard. Then if the plotting, if the result we have here fall into the specific cubicle, we can have the root cause of the problem, like in this table. Here we have the cubicle for PD, partial discharge. D1, D2 is a discharge with low or high energy. T1 to T3, that the thermal force at low to high temperature. The shortcoming of these methods is sometimes the calculation, the final result may not fall into some cubicle here. It's fall to nothing because sometimes we have the combination of more than one force in the transformer. So the ratio of these two gas may not representing exactly what happening this standard. Then the final plotting in this 3D coordination will not indicating any detail. So this method we use less compared to this one. We have the um, another methods because Dover triangle. So with the Dover triangle, we consider the ratio of three gases. Here we have a triangle with we consider methane CH4. We consider the ethylene C2H4, and we consider uh, acetylene C2H2. So the content of the percentage content of the of each gas in compare to the total content of all three gas will be represented in on each edge of the triangle. Then on each edge of the triangle, we have the calibrated from 0 to 100% scale. Then on clockwise, we have CH4, C2H4, and C2H2. Then we determine the percentage of each gas. We have the plotting here with we make some line in parallel with the previous the edge of the in the triangle. Finally, we can find one point uh, for each composition of three gases, percentage of three gases is corresponding to a unique one point here. Then in this triangle number one, we have seven specific zone representing seven force in the transformer. Then if the point we have here fall into any specific zone, then we can have here on the left side, you can see that we have here the root cause of the problem with T1 to T3 for thermal force. Then we have partial discharge, PD, then discharge low and high energy. Here on one note is on top of the triangle that we have a very small part, some small zone. It's presenting the problem with partial discharge in the transformer. So this zone is very small, but the frequency we have this problem in transformer is not small. It depends on the force we find in the transformer. So for thermal problem with the we found this number one triangle. We have two other triangle supplemented for this number one triangle. So for partial discharge at this zone, PD, T1, T2, and here we have another triangle number 4 to have more detail on this. So if the result is a fall into this three zone, PD, T1, and T2, we may have a more detailed analysis on triangle number 4. And if is fall into high temperature force in T3 or medium thermal problem T2, these two zones, we have supplemented triangle number 5. So we can have more information on that. Okay, here we have Durer triangle number 4. We consider the ratio in percentage of other gases to determine what is the problem. Here we consider hydrogen. Then on the next edge of the triangle, so we consider methane C84. Then we consider ethane C2H6 on the other. Similarly, do the analysis to triangle number 1. We can have here some detailed information as the straight guessing in oil. Straight guessing is generated from the oil is not because of the force. Then we have O. We have O zone here, indicating the overheating. Then most serious problem is the carbonization. We have this zone here. It's indicating the problem with cellular material. This this zone indicating a serious problem. Similarly, for Duval triangle number 5, we consider methane CH4. We consider ethylene C2H4, and we consider also ethane C2H6. Then we similarly we plotting in this triangle, and we can have more information with the specific zone. Okay, so similar to Duval triangle, so we have another method here is the Duval pentagon. With Duval pentagon, similar to what we do with Duval triangle, but here we consider all the gases, all 5 gases we have in DGA, and we plot in a pentagon like this for each gas we have here on each S of the pentagon. Then finally the point will fall into the specific zone here, will indicate the problem we have in transformer. This method is more complicated, and typically we use the computer software to plot and to have the analysis result on this pentagon method. So in overall, we have some methodology to interpret the information we have from DGA lab, then to determine the problem in the transformer. We have a key gas method. So this method we consider the the gas limit for each gas and the condition of the transformer. So if typically with the procedure that we use the key gas methods, we consider all the gas limit. Then if no gas over the limit, it's okay. Then no need to do anything else. But for any gas or TDCG is over the limit, we move to directly to Dover triangle or Dover pentagon method to have the further analysis. So with Dover method, you have Dover triangle number one, number four, number five, and you have also the pentagon, Dover pentagon, to do the analysis and to determine the root cause with the DGA. Okay, so by analyzing the by doing the analyzing of the fault gases, we have the information. We can determine the problem in the transformer. Another also very important assessment is the insulation in transformer. So most of the oil immersed transformer, the insulation we use is the class A. Then the insulation material is the cellular material. So in chemically, the cellular material is a chain connect of many molecules connected together because polymer to that to create a very long chain of molecule. The polymer is the chain with many molecule connected together to create the cellular material. Example, the popular material in cellular material in transformer is paper, graph paper on winding. So the strength and the quality of the insulation of the cellular insulation material in transformer is depends on the length of the molecule of the polymer. Then if the we have 1,000 molecules connect together to make a polymer, it's a good quality of insulation. However, during the operation, with time under the attack of high temperature, under the attack of oxygen, of moisture in oil, and acids in oil, then the polymer will be broken down. It's broken into shorter polymer molecule. So the molecule connect together become less and less, and the paper become more is brittle. Then the quality reduce. And here we have the DP. The DP stand for degree of polymerization. So here we have the value from a very good one, the new transformer. Typically, we have 1,000 to 1,200. The value of DP is more than 1,000 is for a good and new transformer. After 5 or 6 years in operation, this value can be reduced and to 600, 700 can be acceptable. Then if this value coming down to about 400, it's an alarming level. We the quality of the material of the insulation is no more in good condition. And in case this value is less than 250, is indicating the serious problem with the insulation quality. And uh, in fact, if this value come lower than 200, meaning we need to consider replacement of the new transformer, or consider to stop, to shut down the transformer and take it out from service. So how to have the DP value? Uh, to have the DP values, we need to have a real sample of paper of the insulation. No way we have to shut down the transformer, open the tank, then take the sample, send to the lab. Then in the lab, they will dissolve uh, the sample into some special chemical. Then by measurement of the viscosity of the mixture, they can determine DP value. So uh, with viscosity, with higher viscosity, the DP value is higher. Then if lower viscosity, and the DP value become lower. Uh, the shortcoming of this method is we need to shut down the transformer to take the sample inside. This one is not easy and not always can be implemented at site. So another alternative solution is to have the furan analysis. So what is the furan? Uh, during the decomposition of the paper, of the cellular material, uh, the molecule, the polymer is broken down, then generate some organic chemical into the oil. That's organic chemical that we call furan. So typically, so we have here five type of furan. Then in the lab, with this method, we just only need to take the oil sample, then send to the lab. Uh, with the analyzer, the lab will take the analysis on uh, all the furan molecule dissolved in the oil. Typically, they use some GC analyzer, some to analyze to do the analysis in oil, and to have uh, the finally the the furan in oil. What we need to take care is we only need to see in the total content of the furan in oil. For example, here in one case we have here, the lab will give us the result in ppb. And here we have more than 1000 ppb. Then here in this table, uh, we have the equivalent, we convert the ppb into ppm. Then we have equivalent ppm of furandehyde to dp value. The higher furan in oil, that means the lower dp is corresponding to lower dp value. Then here you can see, if you have more than 10 ppm furan in oil, that means the equivalent dp is less than 250. Then that is the critical situation. So to do the assessment on paper, first we can roughly we can look into the DGA to see the content of CO and CO2 in oil. Is the first sign of deterioration, the paper deterioration. Then if the oxygen and sorry, if CO and CO2 is abnormal, so especially if we consider the ratio between the CO2 per CO is less than 3 or over 11, is indicating the problem with the paper aging. So to have more detail and to have clearer, more precise, more accurate analysis, we need to do the Furan test on DGA. Then if the Furan indicating something wrong, then we need to do we might need to shut down the transformer to have the DP test on the actual sample. Here we also have to understand the factor uh, impact to the lifetime of the material, of the insulation material, of the cellulose. Uh, the cellulose material, as I already explained, is will be impacted by high temperature. The higher temperature, the higher aging rate of the material. Uh, the other factor also accelerating the aging of the material is the oxygen in oil. Oxygen come from the atmosphere into oil. Uh, More dangerous is the moisture and the acid level in oil. So from where the acids come from, the acids may come from the oil oxidation. The oil aging may create the acids, but also the insulation material molecule broken down, and the aging of the cellulose material also generate acids, also generate oxygen, sorry, also generate moisture in oil. So that is the closed loop. The moisture content, the acid level in oil uh, is again is the factor accelerating the aging of the cellular material. So if we found some very high oxygen content in oil, we found high moisture or acid level in oil, we might need to do the oil reclamation. We may have uh, to do the filtration of the oil as the circulation. We install a circulation loop to take out the oil, filter, then fill it back to the tank. Okay, so that is the very roughly the uh, methodology and what we are doing. We have to do with the DGA and with the assessment of the force and the cellular material in a transformer.